This is screencast 11.1, in which I'll find the normal modes of oscillation with 2 degrees of freedom. Here I have supposed 3 springs connecting 2 masses. I have supposed the spring constants to be K, same for every spring, and the mass is M for both of them. Here the oscillating springs are K1 and K3, and K2 is a coupling spring. So since K1 and K3 are the two harmonic oscillators, here the degree of freedom is 2. So I have supposed x1 to be the stretch of spring K1, and x2 is the stretch, or x2 is the stretch from the original position of M2. So with that in mind, the equation of motions of M1 and M2 are these two masses will be described over here. I have supposed x1 to be greater than x2, and this is just the application of Hooke's law. Rearranging the above equation, I get these two equations. Since this is the springs are involved over here, the result is expected to be oscillatory. Therefore, what we can assume is x1 of t equals to some amplitude times ei omega t, and x2 of t is equals to a2 times ei omega t to be our solution. With that in mind, the equation of motions of m1 and m2 would be given by these two equations. Here the second derivative of x1 of t is applied in this case, and x1 and x2 are replaced by these equations in these two equations, and then we get this. And rearranging that, we get these equations. And for these two equations to give us the solution, the determinant of these two should give us 0. That means here for a solution the determinant of those pair of equations must be 0. Then we get this determinant form, and then solving the determinant we get two frequencies where omega 1 is equals to square root of k over m, and omega 2 is equals to square root of 3k over m. These two frequencies are called the eigenfrequencies, or the characteristic frequency of the coupled harmonic oscillator. And for the first normal mode to exist, the this k, where k is a matrix, minus omega 1 square m mass, this is m is also the matrix of masses, times the amplitudes of x1 and of t and x2 of t should be 0. And solving those two with putting omega 1 as square root of k over m, we get a1 minus, we get these two equations where a1 minus a2 equals to 0 and minus a1 plus a2 equals to 0. Those two are the same thing, so we can say a1 equals to a2 equals to a. Putting the value of a1 and a2 in our original supposition, we get x1 of t is equals to a ei omega 1t, and x2 of t a ei omega 1t. Here the amplitudes are same and the phase difference are also same. So what we can say is x1 and x2 are in phase. Similarly, let's go ahead and find the second mode. For the second normal mode, again we put second eigenfrequency, and then solving the matrix multiplication we get a1 is equals to minus a2. So now in this case x1 of t is a and x2 of t is minus a times cos omega 2t minus delta. That means now these two are out of phase with each other, and let me show that in bpython. Here is the code, and I have supposed the spring constants of all those three springs to be 15 Newton per meter, and masses are 4 kg. Let me go ahead and show you the result. Okay. Oh, it seems I have kept it for the second normal mode. This is the second normal mode, and as you can see, they are out of phase. This is the graph of x1 of t and x2 of t, and let me show you the first normal mode. Okay, this is the first normal mode, and as you can see, there's on it seems like there's only one graph, but that is two graphs exactly coinciding with each other. That means they are in phase with each other. And that's it. That's how I found first and second normal mode of the two uh, freedom of harmonic oscillator with 2 degree of freedom. That's it. Thank you.